So our last section in Unit 7 is all about complex numbers. So up until this point, I've told you we cannot square root negatives, but you actually can in math. It's just not a real concept. We can understand that the square root of 9 is 3, whereas the square root of -9 doesn't really have a real context, which is why we get into this phrase of complex numbers. And we're starting with the imaginary unit, which we use as I. So the square root of -1 is referred to as an imaginary unit, which brings me to my next point, is that we can also consider that if we were to square both sides, you have to understand this is the way that I've been mentioning it, is that the square root and the square would cancel out. So this I squared is actually equal to -1. And I can also continue that and get you to understand that I cubed is actually equal to -I, which probably seems weird, but stick with me for a second, because you could think of I cubed as being I squared times I, right? You add your exponents. 2 plus 1 is 3. And if I squared equals -1, it's -1 times I, so you get that. And in the same fashion, you can also think of I to the 4th power as +1. And I would just explain this as taking I squared squared, because I squared squared is I to the 4th, and what happens when you square -1? You get +1. And what's really interesting about this is I to the 5th power, if I keep going, is actually equal to I. And you can think of I to the 5th as I to the 4th times I. Remember, you add your exponents, so this is true, and I to the 4th equals 1. And so I to the 2nd equals I to the 6th. I to the 3rd equals I to the 7th. I to the 8th is equal to 1, or I to the 4th. And I to the 9th, we're back at the beginning. I to the 10th, I to the 11th, I to the 12th. And it's really actually pretty nice when you examine all of this, is it happens in a perfect cycle. So if you think of this, we're starting at I to the 0. Anything to the 0 power in our context right now is going to equal 1. And then you can think of I to the 1st up here, and then I squared over here, and I cubed over here, and I to the 4th. We're back at the end of our circle, which without proper context, this probably doesn't make a whole lot of sense. But you can see what I mean by it repeats every 4, quarter of a rotation. And that visual might help you when I get to the very last example. Okay, so real quick, when you're doing this now, we're going to do the simplest radical form, and we're going to break this down. And pretty much this is the same thing as when you see a negative inside, you just pull an I in front. So it's I square root of 4, but we know the square root of 4 is 2. So this answer is 2I. Okay. By the way, I put a little hook on my I because we usually have like an italicized I, which I'm sure you guys have seen in previous years, so it's probably not that surprising. So as I look at the next one, you'll also notice that I put my I's in front because I like to distinguish between where the square root is and where my I is. But we don't know the square root of 7, so we just leave our answer like that. Whereas if I look at the next one, we can break down 18 as 9 and 2. 9 breaks down as 3 and 3. So you have a pair of 3's to bring in front. So this negative accounts for this negative. This 3. This negative accounts for my I. And then root 2. Because it did not have a pair in there. Okay, so make sure that you take care of the I's first. For instance, before doing anything, just rewrite this problem as I root 5 and times, because that's what that is, multiplication, I root 6. Because then it kind of makes sense, because multiplication is commutative, you can switch the order around, that we have I squared root 30. But then to understand that I squared is equal to -1, which I already explained, so hopefully you're okay with that I squared equals -1, so this answer is negative root 30. So I cannot emphasize it enough. Take care of the i's first, because every year I have somebody that says, oh, a negative times a negative is positive. That's not correct on this problem. So as I move on to the next one, and maybe I can hurry up. I don't know if you really understand. The square root of 9 is 3, so this is 3i. Square root of -1 is I, or 1i if that helps you. So we're looking at 3i squared. And remember, I squared is -1, so this answer is -3. As I move on to the next one. Again, I would probably just take care of the I first. Don't worry about doing simplest radical form first. Times I root 5. Because then as you multiply, you can multiply the radicals now. That's the square root of 625. And maybe you're good, maybe you're not. But this is exactly 25. If you're not using a calculator, you can factor tree that down and get the correct answer. And then this last one in example 2 is just take care of the I first, and then worry about dividing the 27 divided by 3. So when you do 27 divided by 3, you'll get the square root of 9 over I. And we do know the square root of 9 is 3. I do believe, though, that most textbooks do not want you to leave an imaginary in the denominator. So you might also need to rationalize this by multiplying top and bottom by I. So we're looking at 3i over -1, because I squared is -1. So you might be considering this answer to be -3i. I'll have to examine a little bit closer, because every textbook's a little bit different. Some let you leave I in the denominator, some make you rationalize and not leave I in the denominator. So maybe that's a question that we can talk about in class. Okay, so just so you're aware, maybe I should explain it on the previous page, is these are all imaginary numbers that we've dealt with. And when you have a real part with an imaginary part, notice that I have a real, A is real, BI is imaginary. The combination of a real and an imaginary is called a complex number. And you treat complex numbers just as you would combining like terms. So as I move on to the next one, you combine real parts with real parts. So 3 plus -4 is -1. -5i plus 1i is -4i. And I have confidence that you all can figure that out pretty quickly. So notice with this one, I need to distribute that negative in there. So this is really 4i minus 3 plus I, which would get me to the final answer. I like to write my real part first, by the way. So -3 plus 5i. And then I think this is pretty straightforward, but subtracting -8 turns into +8, and this is the real part. So -5 plus 8 is +3, and there's nothing to combine with that -2i. By the way, every real number can be written as a complex number, same with any imaginary, because b could be 0. So a real number could be like 3, well 3 plus 0i could be that standard form of a complex number. Let's change colors just to change colors, because now we're multiplying. Just like you would any monomial times a monomial, -4 times 5 is -20. I squared. But remember, I squared is equal to negative 1, so negative 20 times negative 1 gives me positive 20. Just like any monomial times a binomial, we're going to distribute. So we're looking at 10i plus 5i squared. But remember, I squared equals negative 1. And just a personal preference of mine, I like to write the real part first. So I'm going to rewrite this as negative 5 plus 10i. But a few things to notice is sometimes we can start with two imaginary things and end up with a real thing, which is sort of interesting. So as I look at the next example, we're just going to distribute, or FOIL if you prefer that phrase. 2 times 6 is 12, minus 2i plus 18i minus 3i squared. Now we have two things to combine, because remember, I squared is going to change the sign of that, so it becomes negative 3 times negative 1 is plus 3. Now I'm going to combine with this. 12 plus 3 is 15. And then negative 2i plus 18i is 16i. There we go. Just a reminder on the next one that 3 minus I times 3 minus I means 3 minus I squared is equal to 3 minus I times 3 minus I. So again, FOIL. I imagine you guys can do the outside and inside terms, together. Plus I squared, negative times negative is positive still. But remember, I squared is negative 1, so 9 plus negative 1 and give me 8. I'm really hoping that you guys remember doing this from before, from Algebra 2. Notice these are, as I introduced to you in an earlier unit, complex conjugates. Notice that the real parts are the same, and then the imaginary parts are the opposite. That's that word I introduced you to before. These are called complex conjugates. So 9 times 9 is 81. The outside term is negative 18i. The inside term is plus 18i. And 2 times negative 2 is negative 4i squared. But why do we care so much about these problems is because these imaginary pieces cancel out, and negative 4i squared becomes plus 4, because remember, I squared is negative 1. Negative 4 times negative 1 is positive 4. So when I combine that with this 81, I started with two complex conjugates and ended up with a real number, which happens. And it will actually always happen, which is why we care so much about complex conjugates. And I don't really want to rush through exercise 5 and 6, so I'll see you in the second video to explain this.